Previously, lesson 5, form 4, topic 4, we were dealing with the second use of the standard electrode potential, which is determining the EMF of a cell. So today, lesson 6, we want to proceed to the third use of the standard electrode potential, which is predicting whether or not a reaction will take place. So we are saying redox reactions which have positive EMF proceed spontaneously, while those which have a negative EMF do not proceed spontaneously. That means the redox reaction which have positive electromotive force, that means can take place. The reactions can take place, while those that have a negative electromotive force do not take place. Those reactions will not occur. That's what we mean. So they require input of heat or electrical energy. So we go examples. So example 1, we are told they have reactions for the reduction of magnesium ion and iron 2 ion are as follows. So we have been given they have ionic equations with the standard electrode potentials. We are told predict whether magnesium will displace. That means we have to take the reaction for the reduction of magnesium to be the reducing agent. So it's the first one. So we can reverse this equation, and we are going to have there magnesium solid arrow, then we are going to have magnesium ion aqueous plus 2 electron. Then we can write the electrode potential value for that half cell. It is positive 2.37 volts. Initially it was negative 2.37. We have now reversed the equation. So that means we are supposed to reverse also the electrode potential value. So the other one, the least reactive metal here is iron 2 ion. We are going to write the way it is in the ionic equation. Plus 2 electron arrow, we are going to have iron metal, I mean. So the standard potential value will be negative 0.44 volt. So we are supposed to add these two half cells. So we're going to say plus. What are we going to get? So here we are having magnesium solid plus, here we have iron 2 ions aqueous. Then these 2 electrons will go with those 2 electrons arrow. We are going to have magnesium ion aqueous plus iron metal, which is solid. If we add the electrode potential values, we are going to have here positive 1.93 volt. So we have gotten a positive EMF value. That means the reaction can proceed. So we can conclude and say the reaction will take place. The reaction takes place since the standard electrode potential value of the cell is positive. It's positive. Hence, or thus, magnesium will displace iron from a solution of this salt, from a solution of it is salt. So that's how we are going to conclude. If you don't want to use this formula, you can use the other formula. The other formula we had, that's if you want to look for the electrode potential of a cell, the standard electrode potential of a cell or the EMF of a cell, this will be equal to E reduction minus E oxidation. We can use that. How are we going to use? We are going to say between these two, which one will be undergoes reduction, the least reactive metal. In our case, the one to be displaced, iron. So iron here is having negative 0.44 minus the oxidizing, the one that undergoes oxidation is the reducing agent, the one that's more positive, or the one that displaces, or the most reactive metal. That's minus 2.37 volts. So if you add these values, still you get positive 1.93 volts. So you can use any of these two formulas. So we go example 2. In example 2, we are told the half reactions for the reaction of silver and zinc are as follows. So we are given the half reactions and the standard potential value of the cells. Then we are asked to predict whether silver will displace zinc from a solution of this salt. So we can take the formula for, if you want to look for the EMF of a cell, it is equal to E reduction minus E oxidation. That's what we can take. E reduction minus E oxidation. So this will be equal to, here silver is the one that's the reducing agent, so it will be the side of oxidation. So that means zinc will be here, the one that will be the oxidizing agent. That means it will be the one that undergoes reduction. So what will be the electropotential value for the zinc half cell? It is minus 0.76 volts. Then we are going to have minus. Then the one undergoes oxidation, it is the one that's now here, the reducing agent, in our case silver. Then that we are going to write positive 0.80. When we put all this in the calculator, what we are going to get will be negative 1.56 volts. So what can we conclude now? Because we have gotten a negative electromotive force, so we can say this reaction. Therefore, this reaction will not take place or will not occur spontaneously. Since it has a negative EMF value. Thus silver, or therefore silver will not displace zinc, from a solution of this salt, it is salt. Full stop. That's what we can say. So number 3, we are told predict whether a reaction will occur between iodine and chloride ions. So here we are having iodine to be the oxidizing agent. And here chloride ions to be the reducing agent. So we can do two formulas. Then if chloride ions are the reducing agent, that means we can reverse the equation for that chloride ions, and we can say 2 of chloride ions aqueous, then arrow, then we can have chlorine aqueous, then plus 2 electron, then even the sign will change. Then this will be negative 1.36 volts. The one for the oxidizing agent, that's iodine, will be just the same the way it was before. We are going to get 2 of chloride ions aqueous, then we are going to have the standard electropotential value, which is positive 0.54 volts. So we are supposed to add these two ionic equations. Then we are going to add. So here we are going to have 2 of chloride ions aqueous plus iodine aqueous. Electrons will go with 2 electrons. Here we are going to get chlorine aqueous, then plus 2 of iodide ions aqueous. So we are supposed to add these standard potentials values, and we are going to get negative 0.82 volts. That's what we are going to get. So because we are getting a negative EMF value, that means this reaction cannot occur. Okay, we can say this reaction will not occur spontaneously, due to it is negative standard electrical potential value, hence or thus iodine will not displace chlorine from a solution of this salt or from a chloride solution.